This is the presentation of our paper long-term visual localization with mobile sensors.
Visual localization aims at estimating the camera translation and orientation for a given image relative to a known scene. In a temporally varying outdoor environment, it is still a challenging problem due to huge appearance disparity between query and reference model caused by illumination, seasonal and structural changes. Fortunately, nowadays, with the popularity of smart devices that come equipped with various sensors such as GPS, compass, and gravity sensor, new possibilities arise for mobile phone pose estimation exploiting these additional multi-modality sensors.
In this paper, we introduce a novel framework, named SensLoc, that localizes an image by tightly coupling visual perception with complementary mobile sensor information. To the best of our knowledge, there is no public dataset for multi-sensor localization under strong visual changes. In our dataset, the experiments demonstrate that our method outperforms the state-of-the-art approach HLoc by a large margin in challenging nighttime environments, while taking only 66 milliseconds to find 2D 3D correspondences on a GPU and 8 milliseconds for PNP ransack. In detail, SensLoc consists of 3 stages, which first leverages GPS and compass to narrow the search space for image retrieval, then builds 2D 3D correspondences in a course-defined manner for query image, and finally solves the camera pose by a gravity-guided PNP ransack. Given a query image, the retrieval stage aims to find a set of covisible images among the reference image collection. Previous method is completely dependent on the expressiveness of global features. When images are acquired from a site with significant visual changes, it may fail. To address this issue, we propose to use the metadata from the mobile sensors as priors to filter incorrect candidates beforehand. We notice that the altitude value of GPS is unstable. So we only use the XY coordinate in reference pose and query prior pose to constrain the search space. Besides, we compute the angle between principal axes of query pose prior and reference images to ensure that camera directions are similar. For a query, assuming that we have obtained its covisible neighbors and relevant point cloud, we focus on establishing 2D 3D matches between subpixels in query and point cloud first. We hierarchically extract coarse-level and fine-level dense feature maps from query and covisible images. Next, every point is reprojected into the feature maps in covisible neighbors and yields a feature track. Finally, an average pooling operation is used for each track to form a 3D descriptor. Based on the query 2D and point 3D features, we initially determine whether a 3D point in submap is observable by the query and search for a rough location in the coarse level. Afterward, the coarse correspondence is refined to a subpixel position by a fine matching module. For the coarse level, linear self-attentions and cross-attentions are used to exchange information between 2D and 3D features. Subsequently, a probability matrix is calculated by a dual softmax operation on the inner product of 2D and 3D features. After that, the coarse 2D 3D correspondences are constructed from the probability matrix by selecting correspondences that meet a confidence threshold and satisfy the mutual nearest neighbor criteria for the fine level. A local window is cropped for each coarse correspondence in the fine feature. After a similar self-attention and cross-attention layer, the transformed 3D fine feature is correlated with all elements in the transformed crop feature to produce a heat map representing the matching probability in the local region. By estimating the 2D expectation over the probability distribution, we gain the fine correspondence position with respect to point. After establishing the 2D 3D fine matches between the query image and the local point cloud, previous works commonly estimate the pose with the PNP technique in a ransack framework. However, such methods may have trouble with scenes containing long-term changes as they highly rely on the performance of local feature matching. To this end, we propose to insert a simple yet effective verification module into a ransack scheme to ensure the correctness of the gravity direction. According to this criterion, we can suppress potential false hypotheses and return high-quality results. As there is no public dataset for multi-sensor localization under strong visual changes, we built a new benchmark dataset. The released dataset SensLoc includes a large city park, containing vegetation, rivers, buildings, and walkways. The dataset construction can be divided into 3 parts: building a large-scale reference map, collecting query images by a mobile phone, and generating GT poses via auxiliary map and joint optimization.
The reference map is captured by a panoramic camera, Insta361, due to the efficiency of 3D reconstruction from panoramic imaging over monocular acquisition, after converting 7,958 database images from panorama to pinhole. Dataset results in 47,748 reference images. In order to recover the scale of the reconstruction and align it with the real geographic world, we pre-calibrated and equipped the Insta361 with a RTK recorder to document the geographical locations. For query image collection, we freely walked through the environment several times after half a year and captured videos using Huawei P40 Pro and Xiaomi Mix 3 smartphones with a developed Android-powered acquisition application. The acquisition app records raw data that measure motion, orientation, and various environmental conditions from the phone's built-in sensors. We found that it was quite difficult to directly generate pseudo-GT poses against the pre-built reference map due to large appearance changes between query and reference images. To solve this problem, we proposed to reconstruct an auxiliary 3D map during the query time,
and aligned with the base reference model using ICP technique. Based on the alignment of two maps, pseudo-GT generation in reference model is equal to recovering accurate poses in auxiliary model. We apply a joint optimization algorithm to find the pseudo-GT pose parameters that meet the requirements: 1. The camera self-localization, 2. Motion constraints from IMU measurements, and 3. Sensor prior constraints regarding translation and orientation. The query capture locations are denoted as the colored points on the map. Besides, to visually inspect the GT accuracy, we project 3D SFM points into the query images using the estimated GT poses, and project the same points in the reference images using the reference poses. We observe that query points are visually aligned to the reference points, supporting that the ground truth poses are accurate. We evaluate several state-of-the-art image retrieval and localization methods on our proposed dataset. We show that the performance of the existing image retrieval methods can be drastically improved by considering sensor priors available in mobile devices, such as GPS, compass. The experiments also demonstrate that our method outperforms the state-of-the-art approach HLOC by a large margin in challenging nighttime environments, while taking only 66 milliseconds to find 2D-3D correspondences on a GPU and 8 milliseconds for PNP ransack. We quantitatively evaluate the influence of image retrieval on SensLock, increasing the retrieval accuracy using sensor-guided retrieval or ground truth markedly increases the localization recall. The ablation study demonstrates that the retrieval stage, which selects local point clouds, plays a critical role in the pose estimation of our method. Thanks for your listening. We provide our paper link and project link below.